In Chapter 8, Section 1, we're going to talk about similarity in right triangles, and we're going to see why everything we did in class today can make sense and be put into a theorem. So by the end of this lesson, you should be able to use geometric mean to find segment lengths in right triangles, and then you should be able to apply the similarity relationships to solve some problems. So remember, in a right triangle, an altitude drawn from the vertex of the right angle to the hypotenuse forms two more right angles. So like we talked in class, you have the big triangle here. There's one of them. And if you draw the altitude right here, you end up making two more triangles, the small one and then the medium one. So you end up with three. And just like we proved in class, the three triangles are all similar to each other. So sometimes you'll be asked a really simple question like, write the similarity statement comparing these three triangles. And if you can do it without rewriting the triangles, be my guest. I like rewriting the triangles just so I can make sure that I get it all right. So the big triangle I'm going to look at first. I'm going to rearrange it so that W is down here, the long side is U, and then the short side is V. So there's one of my triangles. And then the medium-sized triangle is this guy here. My right angle is at Z. The long side is U, and then the short side is W. And then finally the small triangle. So I'm going to flip it upside down basically. And you have my right angle is Z again, and my short is V, and my long is W. So then it's really easy to see from this what parts are similar. So when we write our similarity statement, we know that we have everything matched up. So the first one, let's start with the right angle. So W, go up the short side, V, and then down the hypotenuse, U. So I went this way. That's similar to the second triangle. We'll do the same direction, Z, W, U. And then finally the last one, again, same direction, Z, V, W. So again, if you can do it without writing out these things, go ahead. But if you need the help like spatially putting it down, it really helps to see that when you write your similarity statement. So then using that theorem, we can prove that our sides have to be proportionate because those triangles are all similar. So we end up with a bunch of geometric means, and this is what we did in class today. The relationships in red here, these are geometric means that we're going to focus on. So again, this is exactly what we did in class today by making some sort of similarity statement between all of these. So these are your corollaries. These are why you don't have to put these three triangles on your paper every single time. If you memorize these, you're good to go. So the length of the altitude to the hypotenuse of a right triangle is always the geometric mean of the lengths of the two segments. So that means this right here, this H, is the geometric mean of the two segments, X and Y. And that works every single time. You could go back to the problems that we did in class and double check that. And remember, the geometric mean is the square root of the product of the two numbers. So they're saying H squared is always equal to X times Y. Now the other two are a little more confusing, but once you look at the picture, it'll make sense. The length of a leg of a right triangle is the geometric means of the length of the hypotenuse and the segment adjacent to that leg. So let's say I want to find out how long A is. I need to find the geometric mean of the whole hypotenuse and the segment right next to it. So the geometric mean of X and C gives me A. Where if I'm looking at the other leg of my hypotenuse, this one down here, this B, it is equal to the geometric mean of the whole hypotenuse and the segment right next to it, the Y. So if you want to memorize these, you can. It'll make your life a little easier for the problems, but if you don't, or they don't make sense to you, you can keep doing it the way we did in class by writing these out, figuring out what proportions you have, and solving. So let's do a problem using what we just found. I want to find x, y, and z. So let's find x first. If we look here, x is right here on the tiny little triangle, the small triangle. Now I know that's related to the 9 and the 6. We can use this corollary right here, that it's the geometric mean, that the altitude is the geometric mean of 9 and x. So I know that 6 squared has to equal 9 times x. This right here is the geometric mean of those two numbers. So we get 36 equals 9 times x. You divide both sides by 9, and you end up with x has to be 4. So that's how big this is here. Distance of 4. Now the other two are legs of this giant triangle that we have here. So let's find y first. Remember that this leg is the geometric mean of the whole thing, the hypotenuse, and the little guy that's sitting next to it that we just found. So we know that y squared is the geometric mean of the 9 plus 4 and 4. So instead of writing 9 plus 4, we'll just write 13. So y squared is 13 times 4, which is 52. And if you take the square root, we got to simplify this. So we know 4 goes into it. So we can take out a group of 2's, and 13 is left inside. So this y here is 2 times the square root of 13. Now the last one that we got to find, z. Z is again one of the legs of this big triangle. So we know it's the geometric mean of the hypotenuse of the big triangle and the one butting up to it, this one here, the 9. So z squared has to equal that 13, the 9 plus 4, times 9. So z squared equals 117. And if we take the square root, we end up breaking this down into 9 and 13. We can pull out a group of 3's, and 13 is stuck in there. So this ends up being 3 root 13. So a little easier than separating all the triangles, but you have to remember the relationships. So let's do a story problem. A surveyor positions himself so that his line of sight to the top of a cliff and his line of sight to the bottom form a right angle as shown. What is the height of the cliff to the nearest foot? So we're trying to find this whole distance here, this hypotenuse. And we know that there's a relationship between this distance here, which is my altitude, and this distance here, which they give us. So we can create one of our little equations. And we're going to use this one here. So erase all this. This here, where we know that the altitude squared is the product of x and y, or the altitude is the geometric mean of x and y. So what that looks like here is that 28, which is our altitude squared, has to be the thing we don't know times 5.5. So 28 squared is a big number, 784, and we're going to divide both sides by 5.5. So we end up with x being about 142.5. Now remember, we want to find the height of the entire cliff. So we got to add our two cliffs together, or our two measurements together. The 5.5 is how tall the guy is. So if we add those up, we get right around 148 feet. So using only two pieces of information that weren't even about the triangle that we had, we can figure out how big that final hypotenuse is. So you should be able to use geometric means to find segment lengths in right triangles and apply those in problems like we just did. Make sure you write down any questions you have, and we can go over them tomorrow in class. Have a good night.